So now let's look at the effect of zeros and understand why LHP 0 is good but RHP 0 is bad. Let me start with LHP 0, and for that I'll redo the same calculations. So I'll just, this is basically 0. I'll erase all this. So if I have 0, how should the system transfer function look like? I'll just assume it is a0 into 1 plus s by some z1. Again, in practice we cannot have a system with only 0, because in the act of introducing a 0, most likely you will have a pole. In practice you will have, you cannot have more poles than, more zeros than a pole. But it's a hypothetical case, I'll consider it. So again we'll do the same thing. What will happen to the sinusoid magnitude? a0 into square root of 1 plus omega naught square by, and the phase, what will become, yeah, plus omega naught by z1. Okay. Again we'll impose the condition that we are looking at very low frequencies, that is omega naught is much smaller compared to your 0 frequency. So how will this modify? If omega naught is much smaller than z1, yeah, so this will, the minus will become plus, this will plus omega naught by z1. So this is a0 times sine of omega naught times t plus 1 by z1. So what you have now is a time advance. So seems like a great thing to look into the future. So why don't I use it to build a time machine? What's the catch? Or what are the catches maybe?
You can't sense how the input will be changing in the future.
I mean, but it looks like if I apply as input like this, that is all correct. But what I'm saying is, if I have a system like this, if I input a signal, the output seems to be like this. So seems like the signal is kind of advanced, right? How is it possible? Sorry? Yeah, that is number one point. This is a hypothetical system, but let us say you can have a 0 on the pole, and we can have a case, let us say, where the zero's time advance is greater than the delay by the pole. Let's say that is doable, let us say. Even then there is something, is there something else here, some other catch there? But that's a good point. Yeah, that's what he mentioned. Let us say we even do that, but even then, is there another catch here? Okay, when I write the output here, is this valid for all time, or I've written it for some specific range of time? It's in steady state. Okay, so actually what will happen is this: I apply a sinusoid, sine omega t u of t. This 0 on the sinusoid starts. You will have some transient, okay, and only in steady state it will look like it is looking like this. It is not as though before you apply the input itself the output has started. If that happens, that is a violation of causality. Okay. So what you have written is the steady state portion. In steady state, yeah, it appears like it is sort of advanced. That is at least reasonable. And to understand what will happen in the transient, let's take a circuit example and see. So let's look at an example. So let me take, or I'll start with this circuit. Let us say this is R1, C1, and let us say the signal is u of t. This is my Vout. So what is the order of the circuit? First order. Do I have a 0 here? Do I have a 0 here? No. So let us say here the input is a step. So let me sketch it here. This is the input in dotted line. So tell me, how will the output look like? How will the step response of the RC circuit look like? Exponentially increase. Everyone is aware. Something like this. This is the world famous RC response. Okay, so this is plain and boring. Let's make it interesting. And things will start to spice up if you just add a capacitor here. Now tell me, what is the order of the system, or how many poles I have here? One pole or two poles? Again, for finding the poles, you short the input. The moment you short it, what can you say about the two capacitors? They are in parallel. I mean, essentially you can only initialize the voltage across one of the capacitor, because when the input is shorted, the voltage across the other capacitor is also defined automatically. So only one initial condition can be defined independently. So first order system. But do you have a 0 here? Yeah, because I can short this capacitor, output is still non-zero. And even intuitively, you see that there are two paths for the current to flow from the input to the output. One through the capacitor, one through the resistor. Both will have different frequency dependence, and at some complex frequency it can add up to 0. And you can quickly compute the 0 location. Let's say I assume that V out of S is 0. Right? So sum of the current through the capacitor and the resistor is 0. What is the current through the resistor? If I call it V in, what is the current through the resistor? Yeah, V in of S by R, R1. What is the current through the capacitor? V in of S times SC1. Sum of these two should be? Sorry, SC2. Good. Sum of these two should be? So now I know V in of S is non-zero. So the only possibility is for S to become minus 1 by R2C2, R1C2. So now I have an LHP 0. So I'll mark it here with LHP 0. Fine. So what I have is now a first order system with an LHP 0. So again, it is a first order system. To sketch its step response, what are the three pieces of information I'll need? Initial condition, final value, and time constant. So tell me the final value first. That is easy. As t tends to infinity, what can you say about P out? So, yeah, I mean, input is 1, why? Yeah, in steady state, capacitors are open, so no current flows. So the voltage here must be same as here, which means in steady state V out of infinity is 1. And let's look at the time constant. And what is the time constant here? Yeah, remember again, time constant is same as finding poles. It's a characteristic of the system. So you zero the input, and the moment you zero the input, C1 and C2 are in parallel. So the capacitance is C1 plus C2 times R1. Done. So what is V out at 0 plus? Zero? Yeah, why? Yeah. Okay, so let's just look at that. So some of you understood. So let us say if I have only this, can the output, what is V out of 0 plus? 0. Output cannot change instantly, and why can't it change instantly here? Sorry? Why can't it flow? I mean, this is a voltage source. I mean, yeah, what he's saying is if the voltage across the capacitor has to have a step jump, the current through the capacitor must be, I mean, impulse, right? So why can't this impulse current flow in this network? This is a voltage source, you can provide any current, right? What is limiting the impulse current to not flow in the network? So he's saying this current has to flow through the resistor. So what? Correct. Yeah, I mean, now if the impulse current flows through the resistor, the voltage drop across the resistor should be what? Yeah, impulsive. But nowhere in this network I have impulsive voltages. I have only step voltages. Okay. So I cannot have any impulse current flowing through the resistor. So that directly contradicts. Here I can't have. So, but if I have this connection, now can I have a path for the impulse current to flow from the voltage source? Through which path? C2. Now I can have an impulsive current flowing through C2, and impulsive current flowing through a capacitor will make the voltages jump by a step. Everything is a step, everyone is happy and consistent, right? I mean, if this argument is not comfortable, you can think of it this way. Again, I am looking at t equal to 0 plus, which is a large frequency or a small frequency? Very large frequency. At very large frequencies, what can you say about the impedance of the capacitor? Very small. So if I have these two in parallel, which will dominate? C2, because that's a very small impedance. So again, at t equal to 0 plus, I can redraw the circuit this way. I have u of t, I have C2. That's it. So now we can see the output is a capacitive division, and what is the division factor? C2 by C1 plus C2. So which means now at t equal to 0 plus, the output sees a step jump. So let's say this is that value, C2 by C1 plus C2, and then it exponentially settles. So now you see that the output is kind of settling faster or slower? Faster than before. Okay. So this is how the LHP 0 is kind of introducing a time advance to make sure that the output is settling faster. It is not as though the output has started to exponentially rise before you apply the step itself. That would violate causality. But what will happen is, if you have an LHP 0, the step response at t equal to 0 plus will see a sudden jump, and that jump will be in the same direction as you want your output to reach also. Okay. So this is how I will say an LHP 0 introduces time advance. So which means if you already had a lot of poles in your network, you would have incurred a lot of time delay. Now introducing an LHP 0 will have a time advance, reducing the effective delay in the system, making it more and more stable. Is that logic fine? So that's what happens. I'll just mark it here. I'll have an LHP 0. I'll just say that it counters the time delay due to poles. Okay. So that answers why LHP 0 is great. It is acting like a good angelic friend. Now let's see why RHP 0 is such a devil. For that, I'll again redo the same calculation. Just a change of sign. You can do it quickly. So RHP 0, I'll say that here I have negative sign. Correct? So what will change in the expression? Yeah, the magnitude will not change. It's a complex number. So this becomes minus. So now you see that everything is minus. So instead of having a time advance, you end up having a time delay. So time delay is good or bad? Bad. And what other component was introducing time delay in the system? Pole. So loosely speaking, having an RHP 0, again very qualitatively speaking, it is like having a pole in terms that it is also introducing a time delay in the system. So that's why it is not great to have an RHP 0.
Sir, is the time delay more pronounced in steady state or in transient?
Yeah, we'll see. I mean, in steady state it is clear. We'll look at what happens in transient. Again, for seeing the transient, it is, let's take a same example. I'll just modify this slightly to make it RHP 0. I'll take the same fellow. So here I have LHP 0 because the current flowing through the capacitor and resistor had the same sign. Both were plus V in and plus V in. If I want to make it an RHP 0, what should I change? Both were plus, the 0 was in LHP. If this has to be in the RHP, what should change in this expression mathematically? One should be negative. So one simple change I'll make is the following. I'll just put a gain of -1 here. right? Then you see that this will become minus SE2 here. So then this becomes an RHP0, right? So now can you quickly tell me how will the step response look like? No, I mean, look at this. At V out of infinity, will it change? At infinity, capacitors are open, output is 1. Will the time constant change? No. Again, I short this. This also gets shorted. C1, C2 will be in parallel. Time constant remains same. At t equal to 0 plus, how can you redraw the network? What will change here? That's it. Correct? At t equal to 0 plus, again the same argument, this capacitor will offer the smaller impedance compared to R1. So this guy will dominate in comparison to R1. So we'll have only this portion of the network active at t equal to 0 plus, which is what I have sketched. So what will change to the initial, I mean, V out at 0 plus? It will go to a negative value. So which means now if I sketch the response, it will actually jump up to a negative value. And from here it will take forever to set. So again, you see that you are much better off when you didn't have any zero. With a single pole, at least you are settling a bit faster. Now in the act of introducing an RHP0, we have actually made it more slower. So again, it can show in general that if you have LHP0, the step response at t equal to 0 plus will see a jump. And if it is an LHP0, this jump will be in the same direction as you want your output to reach. But if it was an RHP0, again the output will see a step jump at t equal to 0 plus, but this jump will be in the opposite direction to where you want to finally reach. It is like we ask for direction from here to somewhere, and that guy says go opposite direction and go back. He's intentionally making you slower.